Let's look at a couple of buoyancy problems. Buoyancy was a topic in Chapter 2, which is fluid statics, and this one is problem 2.108. We have an iceberg that's floating in water, and we want to know what percent of the iceberg is underwater. So buoyancy problems are important whenever we have an object that's either partially or totally submerged in the water. In this case, we're partially submerged, mostly submerged. The tip of the iceberg is up top. The force of buoyancy on this object, this expelling force that's trying to push it out, is given by Archimedes' principle. Remember that? So the force of buoyancy is equal to the volume of the object that is submerged, so just the submerged part, and the specific weight of the fluid that is displaced. So it's not the specific weight of the iceberg, it's the specific weight of the seawater around it. So in that case, because it's a static problem, we just have an equilibrium between these forces. Buoyancy force is equal to the weight. And so buoyancy force is here. Weight is the volume of the ice times the gamma of the ice. And if we simply equate these two and do a little algebra, we see that even though we don't know the volumes of the submerged part or the total iceberg, we can get the ratio from the gamma ratios, and that turns out to be about 90% of the iceberg is underwater, about 10% is above the water. So let's look at another one that's more of a thought problem. In this case, we have a 2-liter bottle here, and we fill it with water, let's say, and inside of it we put a test tube upside down. So we have a little bit of an air pocket in the test tube. So what happens when you squeeze the bottle? Why? So at time equals 0, we have a problem similar to the iceberg problem. We have the force of buoyancy, which is equal to the weight of the tube. And that force of buoyancy has to do with the volume that the tube displaces. So that volume is not just the glass part of the tube, it's the glass part of the tube plus that air that's in the above the water line there. So let's say then at T1 you squeeze that bottle and the pressure in the bottle increases, right? Because you're reducing the space in here by squeezing together the bottle. So there's the same amount of air in there, so it's going to go up in pressure. So no more air can enter the tube because it can't get through this pathway here. It's not going to jump through all that water. So instead, water is feeling more pressure above it. It's going to be forced up into the tube. So this means that less volume is now being displaced, right? Because that tube is just going to sink a little bit as more water moves up into the tube. The tube itself is going to drop a little more. And in fact, if you squeeze hard enough, you'll see that the tube will begin to sink. So you're essentially causing the buoyancy force to decrease while the weight stays the same. So think that through a couple of times and see if you can follow that. I have a little toy called Dive and Tony. You may have seen toys similar to this, diving submarines and things. And I'll try to remember to bring him in on Thursday so you can see that this works for yourself. That's it for this one.